components of our mathematical physics is the use of complex variables. And this lecture today is an attempt to teach it better. If you have had a course in complex variables by a mathematician, that would be very different from what we're going to do today. So I want to connect everything that we do with something physical or economic. We'll start off just by showing you a clever way to explain the constant E. Pi is real easy. You just get a circle and show a diameter and wrap a string around it. But the E is a little more difficult to introduce, and you're all going to be teachers probably one way or another, either being paid for it or on the side. So this is one thing to, I think, keep in your mind. But just out of curiosity, let me ask you, if I were to have 100% interest, a bank declared it had 100% interest, it also told you that they were compounding the interest once a second, and you put $1 into this account for the economic period, say 1 year, how many dollars do you have at the end of that time, within a penny or two? Does anybody have an answer for that? Is this something that is on the tip of your tongue? In other words, have you seen a presentation sort of like what we're going to get today? Nobody?
About $2.
You're close. $2, and well, we'll show you. It's $E. That's what I want to get across just in the first part of this lecture today here. So the other thing I want to go through, and this is for lecture 12 and 13. These are the answers to a question that I think needs to be given whenever you use, and particularly in quantum mechanics. Why are we doing quantum mechanics with complex variables? And so the answer to the question, what good are complex quantities? I can give you about 16 answers that are pretty powerful. So this is an important subject, mathematical and physical. And it's entered already in the discussion of the oscillatory orbits inside the Earth that we made up using phasors. And phasors, velocity and position, is what we had. Actually, a velocity divided by omega to make the trajectory circular, but the best job for that problem is complex numbers, real and imaginary. So that will have its complex numbers like vectors, but they're also numbers that provide a phasor clock. Okay, so as we go through this is where we'll really be answering those questions. But first, how did these things come about? And what comes after them? We're going to be generalizing complex numbers in this course when we get to Unit 4. Worthwhile seeing what the original is. So this is the first question that I would present to you, and this involves, let's just look at the first part of it. And this sort of occurred to me when I spent a few years in Brazil. And in Brazil, the interest rates for 1 year were 100%, very close to 100%. Actually, they went up to 120 for a while, dropped down to 90, and then back to 100. It's kind of an interesting experience. Your money kind of evaporates. So to prevent all of the faculty from the university from leaving, every January they would simply jack up they would literally pay you to bring you back to roughly roughly 0% interest, or that is in decay of your funds. So in January, oh boy, this is really great, we've got all this money now. But by March, you're realizing, ooh, we don't have quite as much as we thought we did, and so forth. And by the middle of the summer or late fall, you're approaching poverty. Well, some kind of poverty. They paid us pretty well, actually. Israel had this problem actually worse for a while. In any case, the basic idea is that you have a factor here that multiplies your capital time equals 0 by something that involves a rate times time. So the percentage rate goes in there as a decimal number, and then that's the way you figure out how much money you get if it's just simple interest. But the improvement on banking that has occurred, that's very much part of our culture right now, is the idea of compounding. And it started out, I can remember when semester compounding was sort of a big deal. I was a little kid, and the banks were starting to do this, advertising it as a good way to get more money in your account after a year. And this time, that adds another 25 cents to your account, because you do this twice with the interest rate, whatever it is, which you multiply by time over 2. You do it in 6 months, and then another 6 months. Well, let's just go through this to see the numbers that arise from doing a little bit more than that. If you do trimester compounding, oh well, 37 cents, that's an improvement. Wow. Okay, this is looking good. Especially if the banks were starting to compete with each other and do more than just a trimester, or a quadrimester, or a quarterly thing. But the basic idea would be that the banks would maybe, and this is a fictional, sort of cartoon-like thing that I propose, is that the banks would show you a rich man with a dollar sign, big cigar, and little necktie there. It has an infinity sign, the idea that we compound a lot. We're approaching infinity. Okay, that's a sort of limit. So the question is, how much do you get? Well, with doing more compounding, the idea of all of this is that there's a big, that advertisement would be a bust. And you don't get much more by doing a lot of compounding. So here's the list that we have so far. We pick up 25 cents by compounding this thing twice, and then another 12 cents by compounding it 3 times a year, and then another 7 cents, you see, only 7 cents if you do it quarterly, and so forth. Let's go ahead and do a whole bunch of it. Let's do it monthly. Okay, this is 12. This is a big jump in number of times you're compounding. Weekly, then still another jump by a factor of 4, and so forth. Excuse me. Let me get this one up to speed. Okay, so you get a big jump when you do a whole bunch. 12, 17 cents is added there. Then a weekly, you get another 8 cents. Do it daily, you pick up another 2 cents each year. But already you're seeing that number in green there. Right? Recognize that 2.718. Okay? So what I'd like to do now is say, well, what if we really take this to extremes? I mean, it's pretty extreme already, big exponent of 8,760 there, if we're going to do it hourly. Okay? So that's the next deal here. This is a really very numerically intensive way to calculate this fancy number that you get as you approach infinity. And that's the number we're approaching there. And the idea is we're taking this m to infinity. This is a limit that is really important for all kinds of things. And it's the natural growth a function that we're going to be developing, both real and imaginary. And if you do here a billion, or well, let's start with a million, okay? Well, that's enough multiplications. That's a lot of multiplications, but this is letting us get the number to 6 figures. Okay, and then with a billion, I'm very close to getting up to 9 figures. That's kind of an interesting lesson there, but it's also a lesson in a really stupid way to get this number. We should be able to get this number more easily, with less arithmetic, less steps on a computer. I mean, a computer can obviously do that, but do you want it to? So, the next thing to look at here is what it is that we're doing here. We're taking a binomial and putting huge numbers for the power in order to evaluate this thing. And when you do that, and make sure you understand that a factorial 0 and a factorial 1 is 1, but beyond that it's just a product of all of the factors, of the factors of the numbers leading up to that number, 3 factorial 6, 1, 2, 3, multiplied together. And the whole thing that makes this work is another limit, that is the limit that as n gets really large, this binomial or this trinomial, or factor, 3-factor thing, will be getting closer and closer to just a power of n. And that makes it powerful. That is, when we do that, then the arithmetic is very small. To get 6 figures here, I really need to do about 12 some quotients. That is, I have to actually make fractions, but add them up, and I get 6-figure position. Just very, very few calculations. Nowhere near a billion calculations or a million calculations that are needed for that. So this is an interesting thing to recognize that's happening as we go through 2 different ways of producing this magic number E. Okay, now let's look at pure power series in general. And this is, as I think I can explain later, I call this getting even with the meanness of learning mathematics. Okay, every child and many students just really hate mathematics, and the mathematics seems to be mean. It doesn't go in your head necessarily very quickly. So what we're going to do here is we're going to get back at mathematics. We're going to be mean to it. Revenge. Okay? Now, before I do that, let's just take a look at what we do when we take a first derivative of some function that we've expressed as a power series. Well, the exponents show up here as factors. That's just the first derivative of a power. And that goes on and on. And if you then do another derivative, this is something we've already done when we were talking about the sine oscillation. So another derivative, the second derivative gives you the acceleration. Now you have factors involving each of the powers that were involved with that derivative in the series. And so forth. Let's get this screen up to speed here, and this one as well. And then remember there was the third derivative, that's a terminology for jerk, when we talked about the third derivative of the sine or the cosine or whatever. This first derivative is acceleration, change of jerk, and then we had a terrible joke about that involved the fourth derivative, and by this time the fourth derivative returned us to the original value, the original function in our case of our cosine oscillation, the so-called inauguration, that's my terminology. I don't think anybody at NASA thought of that right away, but anyway, that's the series that you have there. So the question is, you have here that any function can be written as a power series, so it appears, and this is an easy way to see that. But one thing you should realize as you teach your sophomore physics, the first three terms there is the formula that you use when you're having a constant acceleration, a gravity trajectory problem or whatever, right? There are a bunch of other things there, but this is really asking for magic. You're saying that I can make any function of time just by knowing these coefficients. I have to know where I start, I have to know what the velocity started, I have to know what acceleration started, and if I want to keep going, jerk, inauguration, whatever you want to call that, revolution, that would be a good name, but so forth. You have a whole bunch of factors here, and the question is, how good are those things? This is just a good old UP1 formula, no problem with that. But can we use this to take care of a sine wave or a cosine wave, you see? That's asking a lot. That's being mean to mathematics. We're going to make these power things sum up to something that waves forever. That's really what you're asking here. So we're thinking about that, just thinking about what that amounts to. That's really quite a thing. And in particular, the exponential. We'll look at that one first, because it's the one that started all of this arguments about knowing the initial values of all of these derivatives and being able to predict the future from that. Is that kosher? Should I even use the word kosher? See, what's involved in having that? That's really quite a thing to be asking about. So, let's go ahead and just plot. This is being mean to mathematics. And we can be mean to mathematics because we've got computers that draw curves for us. So we're going to see exactly how many terms that you need to make a wave that waves for a long time, several periods at least. So, exponential doesn't look like it's having much of a problem here. First you have a constant, that's 1, okay. Then you have a slope of 1, okay, right there. That's your first approximation. Then the second approximation, I call this one the 0th approximation. The second approximation actually has a nice little parabola that's sitting right there, okay, giving it the curvature. Okay, and then so forth. As I go through each of these, I get a third degree parabola, or whatever you want to call it, cubic, and then a quartic. That's that orange thing there. But each of these peel off of the exponential pretty quickly. Okay, the actual exponential is this red curve. And you see all these others saying, "Oh, heck, I can't keep up with that exponential. I'm out of here. I'll go to infinity another way," and the same thing on this side. So that I think is, it doesn't show very well on that screen. We did a black and white one that comes on the computer program that went with this when I first started doing this. But there are, that's the situation for the exponential. The next one is really crazy. This is something I haven't seen anyone just do this. And it's so easy to do now that you have calculators. The plot. Let's do the cosine. The cosine turns out to not have any odd powers, because cosine is a nice even function. And by the same token, the sine is an odd function. That is, change the sign as I reflect through the origin. But it has a similar structure to the cosine in terms of when these various curves, in this case the first one that's not 0 is a inverted parabola, a little 1/2 in front of it, and you can see that it sort of peels off before we get past about a half right here. And it's out of here. Okay. Then I go for the fourth, okay, the fourth degree, the quartic. That's this thing. That's a beautiful curve. But it doesn't stick right. It goes, about one of these squares, or two at the most, before it just says, heck with it. I'm not going any further. Okay, so what's interesting is the distance that you go each time. Here's the sixth degree even function right there in turquoise. And then in this sort of green, yellow-green is the eighth degree function. You see, each time the peel-off distance, looking at just where I actually see a pixel difference, is the same. This is going to go on forever. Just go to higher and higher polynomials. They'll go along very, making the curve very precisely, and then boom, they're out of here. Now this is, I think, an important lesson, because what we do in quantum field theory is we approximate by perturbation theory, which are polynomials in the various quantities that we are trying to find. And what we're doing is we're working with a wavy system. That's quantum mechanics. It's also classical mechanics, and you work with oscillatory objects. So is it any surprise that perturbation theory is has been a pretty poor customer for us? This really is where you see it for the first time. Okay, so that's one lesson that I'd like to make sure that you have a chance to see before we go on here and actually make use of combinations of cosine and sine that give us the complex exponential. Okay? So, we consider here some more things. And by the way, you might have noticed on the very first page here, a little mention up at the top there, the word interest, as opposed to interest, is British. It's a British spelling, is the way, and it used to be, we use this in this country, I can remember, when you were marked off for spelling interest as interest. So when you go to the bank and you say, I am interested in your interest rate, right? Don't have to do that anymore. You say, I'm interested in your interest. This is something weird that's happened nobody ever talks about. I Google it and everybody's just perfectly happy with interest. You go further down the list and you discover the Brits have still stuck with interest. It's easier to say, right? Isn't that strange? Okay. More funny business later. What we do here is go ahead and work with imaginary interest. Now, when you are talking about imaginary interest, that sounds illegal. When somebody's cooking the books, right? One day it's up, the funds are up, when they're negative, they quickly cover it up before the bank examiner shows up and it's back to positive, right? That's what you get with imaginary interest, with oscillation. Kind of a crazy way to say it, but yeah, that's what's happening here. I just go through here and every one of the squares, or even powers, drops me down to this, and the odd powers drop me down to this, with an I for every one of them, because I squared, I cubed, I fourth, I fifth, just go to the 4 points of the compass, and then they return. Okay, so that's an important thing to remember, particularly when we generalize this imaginary number to PHYS spinors. This is going to be a wonderful exercise of doing things in 2 dimensions. The PHYS spinors let you work in 3, actually 4. So that's, that's the real deep lesson that I'm trying to sell you with as we talk about these things. So this particular relationship is going to be generalized for Unit 4 in order to do oscillatory mechanics and rotations and all sorts of other things that pop up when you take that magic step. This magic step was taken by a German, Euler. Actually, I'm not sure it's German. Thinking just now that he might have been Swiss or some. Well, anyway, it doesn't matter right now. This is definitely French. Here and there got their contribution. But the generalization that does the spinners, it wasn't named that way when it happened, is by Hamilton. Hamilton discovered what are called quaternions. So he had more than just 1 and I. He has 1 and I, J, K. Those are his notation. Which Daniel Kennefic now says his inscriptions of his relations that had quaternion structure and eventually spinner structure, he was so happy about it that he literally took out a knife and carved them into a wooden structure of the bridge over the river in Dublin. And now that has been taken down and made into a museum, and that's what Daniel told me, is that now it sits in a museum. When I visited, it was still on the bridge outside in the rain. Okay, so phasers and all of that kind of stuff is what this is letting us do immediately. And we've already talked a little bit about this being position and that being velocity divided by omega. That is a phaser that wouldn't involve complex numbers or any of the imaginary stuff. And we wouldn't call it the imaginary axis, it'd just be the velocity axis scaled by omega. But we come now to use those directly. We imagine the whole field of spinners when we talk about quantum mechanics. And the other thing that's important about complex numbers, besides being a wonderful physical realization of phenomena that's oscillatory, is that it helps you with your literal algebra and trigonometry. And if you ever have some sort of exam where you just have completely slipped your mind, don't remember what cosine of a plus b is, well, you do remember that e to the I a plus b is e to the I a times e to the I b. So you only have to multiply these two together to get the real part, which is this, and you get a minus sign there because the i's get together to make that particular term. In the price of this, you get two for one. You also get the sine of a plus b. Okay, so there's a lot of things that we do where we don't have to go through this rigmarole when we're working with the exponentials that you would normally have to do if you're really putting the waves together in their real form. Okay, well, that's one thing that is a help. Here, complex numbers add, like vectors. That's very important. It's a linear system that we put together to make. And we get the magnitude of the sum that's called cosine law very quickly. We also get sine laws and things like that. But, we'll talk about that later. But the basic idea is the sum and the difference of two complex numbers. We look and we see what those are. There's the sum right there, and the cross thing is the difference. So it's simple geometry, and we read off the answer just by knowing where the sines and the cosines really are. So that's good. Phasor clock, I won't go through that again, but the basic idea of having a real part of a psi, a quantum number, and then the imaginary part, I call it the is and the gonna be. You guys are probably too young to remember when Clinton was being quizzed by the prosecutor over his little affair with Monica Lewinsky, and he said, well, it depends on what is. And what he was talking about is what are the traditions for covering women in Islamic as compared to what we wear in the Western culture. But everybody made fun of the fact that you didn't know what is, so that was the main message that came out in the media. But this is the gonna be, and that's if you do what he did, you're gonna be in trouble. So you can think of the imaginary part as a prediction of the future. It's going to be. Okay, that's all well and good, I think. But let's just take a quick look here. I'll do this one ahead as well at the structures that are coming out from this. There's a Cartesian form, there's a polar form. And polar coordinates is one of the coordinate systems that's going to be given to us immediately as we play with the exponential functions here. But having these relations, and these are all going to be generalized, you see, in the spinners that Pauli and Jordan discovered, well, about almost a half a century, I think, more than a half a century after Hamilton got it the first time. So that's one thing. Now, here's some vector analysis. If you're teaching somebody vector analysis, complex numbers, at least for two-dimensional vector analysis, are really nice to bring up. It gives you the cosine, sine, minus sign matrix that is a rotation. So the basic idea is if you have a complex number x plus I y, then e to the I phi immediately rotates that in exactly the way you would want it to. So you have to multiply cosine plus I sine times x plus I y. That's easy to do. Result is a real part and an imaginary part. So those are two components of the rotation that are sitting there. So if you were to write this out in Gibbs notation, you see, where there's a unit vector x and then there's a unit vector y, okay, that's what we're looking for here, and then that can be expressed this way, that is as a matrix that multiplies x and y and gives the rotated components directly. But this is so elegant, you see, and a nice way to explain it. Another example of automatic trigonometry. So, am I making enough of a case for complex numbers? Okay. Well, we have to make a case for complex functions too. This is a start right here. Okay? And this is just showing differences and all that kind of stuff that show up when you have two rotations and all of that. Okay? This is a vector representation of that, just to make it absolutely clear. And this is what we're going to do a lot of for the next, well, for the rest of the lecture, is play around with different ways to look at old notations and then this complex thing, treating it as something new, which it isn't, of course. But scalar product, vector product, you get them for free. You start with a vector as x and y component, and another vector that has a bx and by. And what you do is you do their so-called star product. Now, what does that mean? In this case, it's really simple. The star goes on the first factor. That is the factor to the left. If we're doing this as an operator, this would be the first factor that acted. But that is here the one on the left, this guy. So you literally take a star, which is taking any i's that are in that vector and changing their sign. You're doing a reflection through the imaginary axis. That's what this means. And bingo, when you multiply it all together, the real part is the scalar product. The imaginary part is the z, big Z, z out of the plane, perpendicular to x and y, of the cross product. It doesn't give you all three of the cross products. That takes a Pauli spinner. But it gives you this much, which is welcome, because that's where you're working in 2 dimensions. Okay? All right. So this also lets you see it just by writing them all in their polar form, which is fair, and then expanding that. Okay? Then you see that the cross product involves a cosine, a sine, and the dot product involves a cosine. Okay. All right, these are all things I think that take a little less effort to teach. And as I say, you're going to be a scientist, you're probably going to be a teacher of some kind, and ought to be able to take this to your young cousin or whatever, or you have a son and a daughter, you know. They'll be less mad at mathematics if they can see this. Okay. And there's the full components showing in the final analysis of this. Okay, so this is the last of the arithmetic that goes with complex numbers. The next step here, vector calculus, complex numbers. What are they? Vector calculus, vector derivatives, and all of that kind of stuff. That's a little bit more involved, as you can see by these first few lines that show up in this discussion. Here's where the partial derivative really makes its appearance, and it's all of its, whatever you want to call it, beauty or ugliness, depending on how you treat it. Once again, we have here two kinds of functions that we could use to describe a complex number, z. We can either just take the two components of the thing, or also we could work with z and z reflected. Now, we're going to have a derivative with respect to z, but also one with respect to z star, because we have derivatives with respect to x and derivatives with respect to y that we understand, but it would be kind of nice to go ahead and make a chain rule here that would give me a total derivative of f with respect to z by simply summing over the two variables that we're used to using, x and y. And that means I have to find out here what is the value of partial derivative of y with respect to z, what is partial derivative of x with respect to z. Okay, so I have to go and look at this and this to see what's the coefficient that goes with the partial derivative of x with respect to z. That's this guy right here, 1/2. So 1/2 goes there in this chain rule, and then what's the partial y with respect to z? Well, what we're doing here is we've got the 1/2, but now with minus I, that's 1/i. Okay, so it's important to recognize that's a derivative with respect to z. This is a very similar one. This one is with respect to z star, with surprise, surprise, that's something with a complex conjugate of this one. So we can invert, or we can just write it as an operator, which I've done at the extreme right hand of this thing, ddz and ddz star. So once you get that stuff out of the way, then you have something that's really powerful for doing a vector analysis of fields, whole fields, and coordinate systems that are part of field. And that's what we're after in this debate, most particularly. So when we look at, say, the real part of this particular thing, the derivative function, that has in it, the first component, is what we call the vector the divergence vector. And then the imaginary part is one of the three components of the curl. And it's that, I put this notation that I leave out finally later on, but I say this is a component of a three-dimensional thing, but that's just because I know it already. This is what we would call the curl of the vector that represents a field. The field is a function now of x and y, so we're doing a full differential calculus of two variables using either the two variables x and y, or sometimes the two variables z and z star. That's what makes this really powerful. If you can get used to that, everything that we're going to do the rest of the lecture here is going to, I hope, be fairly clear. So this is a difficult part right here. This is something that bears some thought and consideration. But this is number 7 in the things that we get from complex variables. And that is that it's really easy to invent source-free 2D vector fields. That is, invent just by writing down any function of z that you can think of you will get a field that is pretty much everywhere divergence-free and curl-free. That's kind of cool. That's kind of neat. So that's why I went to trouble today to set up an old program that shows complex variables. It was called Analyte, and TC is now trying to bring that kicking and screaming into the HTML world, and also having features that are well beyond what I'll be showing you with the old-fashioned Analyte. So pretty soon you'll get to be able to work with that and not have to go somewhere and get a Mac that can run System 9, which is very long and old to go. Okay, so we invent these fields simply by take any function you can think of, z squared, z to the first power. Z to the first power is already an interesting field. Okay, conjugate it, that is, change its i's to -1. That will give you a complex function of a complex variable that has been conjugated, for which, and this is the important part, the derivative of this thing with respect to z is absolutely 0. So that makes the components of it have no value, that is, be 0. That's the trick, right there, that we're going to use over and over again. Make coordinate systems or fields or all sorts of weird things, okay? Things that don't have to be so weird. You can see through them. So this is it. Is there any questions about this? Because here's where we do something kind of weird, and we're going to demonstrate it just with the function of z equals z. The field equals z. Okay? That's the example right there. We'll put a constant on it if you want. We're just going to put 1 on it. But our idea is that this thing is not a function of z, so it has 0z derivative. Okay. Now, that means that when we write down the vector in the ordinary, first of all, matrix notation, or the ordinary Gibbs notation for the x and y components, that's what we're using. We're using the f star of x and y. And this particular guy right here, this is the z star here, so we're going to be using, if it's z, we're going to not just be writing down x and y, we're going to write down x and minus y. Okay, and then look at that, just to check it very quickly, that it's divergence, absolutely nothing. They cancel, these two terms cancel here. And the same thing's true with the curl. Partial x of y minus partial y of the x component. Okay, both of those are nothing. Okay, so this is, we call it DFL, and let me get this on the other screens in case it's hard for you to see the very bottom. DFL just means divergence-free laminar. That's a common name for a field that doesn't have any of these two derivatives. It has 0 for those quantities. Okay? There's an example. That's what happens when you take this particular function, just a times z, and conjugate it, and then draw vectors at any point that are given by the functions that we have written right here. These are the vectors here with a equal to 1 being plotted. Now I've set up this other projector here, which is really bright, so I can just wash that screen completely up without me having to turn it off or anything. But that's what we're going to be looking at. And this is one that you would want to turn off because this particular projector isn't doing very well. Well, this computer isn't doing very well at handling color. And there's something weird going on there. But when it comes to plotting these things, we try to do it in an educational sort of way, an intuitive sort of way. So the basic idea here, now this is 8, is that I can immediately find the potentials, and I say potential plural, that go with these things. Go ahead on this one just to get it on this screen here, and also right here. And I'm interested in this one, dragging the A to the side there. But anyway, the idea is that this DFL, these lambda fields, divergence and curl-free field, has both a scalar potential and a vector potential. And you can use either one or both, or any combination where the coefficients add up to 1 of these two through gradient and curl, get the original field vector back. So you start, a complex potential has both a scalar part and a vector part. Now it's not vector in the sense that we're used to. Better to say this one is a kind of a force field. This one is kind of a streaming something or other. Well, this will become clear as we look at these things in some detail. Just this very simple one we look at in detail. So this thing exists so that the complex potential exists so that the force field is the derivative. Now remember when we talked about the force field being a gradient of a potential, we put a minus sign on it because we're physicists, right? I do not put the minus sign there. This is where it really started, the whole idea of technical development in mathematics of a potential for a function. They didn't want to put a minus sign on there because they weren't even thinking about force and potential, really. So we won't either. But if you want to make connection, then you put the minus sign. So this is the force to hold back, right? Not the force that makes it go. It's just the third Newton law at work here. The hold back and what it makes it go are just opposite signs of each other. Okay? All right. To find this, we have to integrate the function. But we only have to integrate a function of one variable. The variable is complex. That's cool. Okay? That's what we like to see when we talk about the advantages of complex variables. So this is what we're going to be doing right here with this. When I integrate AZ, I get Z squared over 2. Whatever the constant is, it could be complex. All that's going to do is take the whole field and rotate it, changing that A to a complex number. But let's just leave it at 1, so we get the field in the normal orientation that you would expect for this particular object. So, I get Z squared. And Z squared is binomial, has a real part and an imaginary part. So there are the two potentials. One scalar that works like you're used to potentials working, and a weird one that you're not used to because we don't give courses in hydrodynamics, but that's the potential that you use. It's called the streaming potential in hydrodynamics. So we're getting both of those to work for us if we want, or we can just ignore this one. Pretend we're, kind of ignorant physicists and never take hydrodynamics. So that's good. That's okay. Now, again, this is probably a moment when I should just go ahead and produce this curve for you on that screen. I'm going to be using it a lot for some more things that we talk about. But let me go ahead and flip on this project. Actually, maybe you could just reach up and there's a power button on there, and we should be able to see a picture of something. It's not showing. There we go. I think that will warm up there. There we go. That's what I've got on this screen right here, I think. Yes. Okay. So this is a kind of control panel that goes with this thing, and right now I'm picking the function, the force field equal to constant A being set by these little dials here, and TC is finding ways to get the control panel on the same screen with the thing, and being able to do a lot more. But just for the heck of it, let me start off with the really simple one. That is f of z equal a constant. And it's kind of what you might expect. So what I'm going to do here is go ahead and plot this function using a black background. And when we click on it, we're going to be able to get the scalar phi lines. So we'll just take this one step at a time here. Let's just go ahead and do it. It is a little annoying to have the projector up there, so I'm going to go ahead and let it, just go ahead and give it a blank it out. Oh,
It's flashing now.
actually take the black button that's to the south and hit it twice. Once, twice. There we go. That's what we got it. Most projectors show up 2 hits. So this is just what you get when you, let's just go back to the main control here. This is what you get if you just set it equal to a complex number, okay, some number. In this particular case, if I were to increase, say, the imaginary part here by a little bit, let's go ahead and increase it by to half or so. If I do that and plot the field, well, I get a constant field, but now it's been rotated. I changed the imaginary part a little bit. That tips it down by giving it an extra y component in negative direction. Remember, this is F star that we're dealing with, so it goes down when I put a positive A. If I put a negative A in there, it would rotate the left-handed way. Okay? So, let's go back to the main control panel here and get rid of that constant. I'll bring that back to 0. And this time I want to go back to this one, and I want to start putting in the scalar lines. Okay? And so and this is the way that, pretty much the way we're trying to make the HTML program.